Hi everyone, today we're going to learn about the logical foundations of mathematics. This is where we build the toolkit for clear thinking, not just in math class, but in any situation where you need to make a solid argument. Think about the last time you tried to convince a friend of something. You probably didn't just state your opinion, you gave reasons. You might have said something like, "If we don't leave now, we'll be late for the movie. We don't want to be late, so we should leave now." That's logic in action. In mathematics, we take this everyday reasoning and make it precise and unambiguous. We strip away the subject matter and look at the pure structure of the argument itself. This allows us to determine with certainty whether a conclusion follows from its premises, which is the very heart of proof. To do this, we start with the simplest building blocks, statements, also called propositions. A statement is a declarative sentence that is either definitively true or definitively false, but not both. Paris is the capital of France is a true statement. 7 is an even number is a false statement. Questions, commands, and opinions like, "This cake is delicious," are not statements in logic because their truth isn't objective. We often represent statements with letters like P, Q, or R for simplicity. Now, we rarely reason with single, isolated statements. We combine them. The main ways we do this are with the connectives and, or, and, not. In logic, these have very specific meanings. Let's define them. The negation of a statement P, written as not P, is simply the opposite truth value. If P is true, not P is false, and vice versa. The conjunction P and Q is true only when both P and Q are individually true. If either one is false, the whole and statement is false. The disjunction P or Q is true if at least one of P or Q is true. In mathematics, we use the inclusive or, meaning it's true if P is true, Q is true, or both are true. Let's work with a basic example. Let P be the statement, "It is raining." Let Q be the statement, "I am carrying an umbrella." Now, consider the compound statement, "It is not raining, and I am carrying an umbrella." In our symbols, that's not P and Q. For this to be true, not P must be true, meaning it is asterisk not times raining. And Q must be true, meaning I am carrying an umbrella. So the only scenario where this statement is true is a sunny day where I have my umbrella with me. If it is raining, then not P is false, making the whole and false, regardless of my umbrella situation. Now, the most powerful connective for building arguments is the conditional statement, usually phrased as, "If P, then Q." We write this as P implies Q. This is the logical backbone of theorems. For example, if a number is divisible by 10, then it is divisible by 5. Here, P is, a number is divisible by 10, and Q is, it is divisible by 5. The crucial thing to understand is when a conditional statement is false. It is false times only when the first part, P, is true, but the second part, Q, is false. In our example, the statement would be false if we found a number divisible by 10 that was not times divisible by 5, which is impossible. In all other cases, when P is false, or when both P and Q are true, the conditional statement is considered true. This can feel odd. The statement, "If the moon is made of cheese, then I am the king of England," is logically true, because the premise, "the moon is made of cheese," is false. Let's tackle a more IB style problem. We are asked to determine the truth value of the following compound statement for a specific scenario. If the triangle is equilateral, then it is isosceles, and its angles are all 60 degrees. Let's break it down. Let R be, the triangle is equilateral. Let S be, the triangle is isosceles. Let T be, its angles are all 60 degrees. Our statement is, if R, then S and T. We must be careful with the grouping. In plain English, it reads as the conditional, if R, then S being true, and the statement T also being true. So symbolically, it's R implies S and T. Now, consider the scenario where we have a triangle that is asterisk, not times equilateral, but is isosceles with angles 70, 70, and 40 degrees. For this triangle, R is false, S is true, and T is false. Evaluate the parts. R implies S. Since R is false, this conditional is true. Remember, a false premise makes the whole if-then true. Now we have true and T, but T is false. A conjunction, true and false, is false. Therefore, for this specific triangle, the entire compound statement is false. A very common mistake students make is confusing a conditional statement with its converse. The converse of if P then Q is if Q then P. These are not logically equivalent. If it is a dog, then it is a mammal, is true. Its converse, if it is a mammal, then it is a dog, is certainly false. Another frequent error is misinterpreting or as the exclusive or from everyday speech, where we mean one or the other, but not both. In logic, unless specified otherwise, or includes the possibility of both. Finally, when negating compound statements, be systematic. The negation of P and Q is not P or not Q. The negation of if P, then Q is logically P and not Q, the one scenario that makes the original conditional false. So, to summarize, the logical foundations give us the rules of the game for mathematical reasoning. We start with simple statements, combine them with connectives like and, or, and not, and most importantly, we use the conditional if-then to form arguments. Understanding the precise truth conditions for these connectives and being wary of the converse allows you to analyze and construct valid proofs, which is a skill you'll use throughout the entire IB course and beyond.